Hello, I am Cikgu Suryati Yusof from Sekolah Menengah Sains Muzaffar Shah. Okay, we are going to learn today topic heat. The first topic is thermal equilibrium. Okay, so what are you going to learn in this topic? First, we are going to explain with example thermal equilibrium in daily life. So the first thing you have to know what is the meaning of thermal equilibrium. Okay, so look at this picture, a cup of coffee. So when a cool metal spoon is put into a cup of hot coffee, the spoon and the coffee are said to be in thermal contact. Right? So heat energy can be transferred between the two bodies. How can the metal spoon cool down the hot coffee? And what is the final condition of the spoon and the coffee? Okay, let's look at these two pictures. Okay, first a boy feels the heat of the kettle. Why? Second, the ice melts when it is in the boy's hand. The boy's hand is cool. Why? Okay, so let's answer the question. Okay, the first one, the boy takes his hand away from the kettle because the boy feels the heat of the kettle. The heat is transferred from the kettle to the boy's hand because the kettle is hot and the boy's hand is cooler than the kettle. Right? So heat is transferred from hot object to cool object. Okay. Secondly, the ice melt when it is in the boy's hand. The boy's hand is cool because heat is transferred from the boy's hand to the ice, and heat is transferred from hot object to cool object. So again, heat is transferred from hot to cool object. Now, what is the meaning of heat? So heat is a form of energy. Remember, we have so many types of energy. So heat is one type of energy that we have. Okay, what is temperature? So temperature is the degree of hotness. Okay, so when you feel 6, your temperature will become higher than 37 degrees Celsius. Right. So SI unit for temperature is Kelvin. Normally we use degrees Celsius, right? But for SI unit for temperature, we use the unit of Kelvin. So we will learn this later on. Okay, so now we compare between temperature and heat. Okay, the first one, definition. Temperature is degree of hotness, while heat is a form of energy. SI unit for temperature is Kelvin, and SI unit for heat is Joule. Now, measuring device for temperature, of course, thermometer, and heat we use what we call calorimeter. Temperature is a base unit ataupun base quantity, while heat is a derived quantity. Now, when an object is heated, so heat absorbed and temperature increases. When an object is cool, okay, heat releases and the temperature will decrease. Okay, these are example: hot object, cool object. Now, so we are going to learn the meaning of thermal equilibrium. So we have first activity to show thermal equilibrium between two bodies in thermal context. So the apparatus, we did 2 retort stand, 2 thermometers, 250 milliliter beaker A and B, measuring cylinder, stopwatch, hot water, tap water, and tissue paper. Yeah. Number 1, wrap beaker A with tissue and fill it with 100 ml of tap water. Number 2, fill 40 ml of 50 degrees Celsius of hot water into beaker B. Place beaker B into beaker A, then place thermometer A and thermometer B into beaker A and beaker B respectively. Then record the readings of thermometer A and thermometer B every 30 seconds until the readings of both thermometers are the same. So here we have beaker A, bigger beaker A, and then we put tap water, and then we have a smaller beaker filled with hot water at 50 degrees Celsius. Then we put it inside the beaker A. Then we take the temperature for the two thermometer. Okay, so this is the result. So thermometer A increasing, thermometer B decreasing until they both have the same temperature. So first question, why is beaker A wrapped with tissue paper? To prevent heat absorbed from surroundings. Second question, describe the changes in temperature of the hot water and tap water. So as we see, so when the two water are in thermal contact, the temperature of the hot water decrease while the temperature of the tap water increase until both objects have the same temperature. Now what caused the changes in temperature? So hot water release heat to tap water absorb heat from hot water. Transfer of heat occurs when the two bodies are in thermal contact. Okay. Alright, so we have this diagram, hot water in beaker in color red color and tap water in beaker A. So describe the transfer of heat between hot water. So heat is transferred from hot water in the beaker to the tap water in with high rate. So most of the heat are transferred from beaker B to beaker A. So heat is transferred from the tap water to the water in the beaker with low rate. Also, there will be heat transfer from tap water to the hot water but in a low rate. The direction of net heat transfer is from hot water in beaker B to tap water in beaker A. Remember, from hot object to cooler object. So temperature hot water decrease and heat release. Temperature of tap water increases and heat absorbed. Now compare the temperature of both thermometer after 5 minutes. So both have the same temperature. What happens to the rate of heat transfer after 5 minutes? The heat transfer at the same rate because the hot water in beaker B to tap water in beaker A. Because both heat transfer from B to A and also from A to B with the same rate. Okay, so as a conclusion, what can we say about the net rates of transfer of heat when the readings of the two thermometers become equals? Yeah, we said that there is no net heat transfer between both readings, no dominance. Both object transfer each heat. So we said that the net rates of heat transfer is 0. Means that both hot water and tap water are in the state of thermal equilibrium. So what is the meaning of thermal equilibrium? Thermal equilibrium means so there is no net flow of heat between two subjects. Two objects have the same final temperature. Okay. Right. A hotter than B. So heat, majority of heat transfer from A to B. Only a minor of heat transfer from B to A. But after thermal equilibrium is reached, both have the same temperature. Let's say 50 degrees Celsius means that heat is transferred both from A to B and also from B to A at equal rates. Okay, so the net heat transfer between A and B becomes 0. Okay, so let's look like example in our daily life. So we have the first one, a wet towel is placed on the forehead of a person who has a high fever. Okay, so what we have here is initially the temperature of the cause is lower than the body temperature of a person, right? So heat energy is transferred from the forehead, which is hotter, to the towel until thermal equilibrium is reached. As a result, the heat energy is removed from the person. So the towel is rinsed in the tap water and the procedure is repeated, right? Okay. Second, cooling drinks. Okay, first we have to put ice into the drink. So hot drink can be cooled by adding a few ice cubes to the drink. Heat from the hot drink is transferred to the colder ice until thermal equilibrium between the ice and water is replaced. The temperature of the drink decreases and the drink cools and the ice also melts. Okay. Okay, so next, cooling object in refrigerator. So when food is kept in the refrigerator, heat from the food flows to the air in the refrigerator until thermal equilibrium occurs. Temperature of the food drops and the food stays fresh for a longer period. Okay. Now in this case, the food gives heat to the air and the food lost heat, so it becomes cooler and stay fresh. Now the fourth one is the baking cake in oven. So this time we need the heat. So what we have here is hot air in oven is in thermal contact with cake batter, right? The heat from the hot air flows to the cake batter, right? And this causes the cake batter to be heated until it is baked. Okay. And the last one, taking temperature of a sick patient. First, a clinical thermometer is placed under the tongue of a patient. Heat from the patient's body flows to the thermometer until thermal equilibrium occurs. And the temperature of the patient and the thermometer become the same. So the body temperature of the patient can be determined because the body temperature equals to the temperature of the thermometer. Alright, okay, we continue with the second lesson for 4.1 thermal equilibrium. So the standard of our standard learning is to calibrate a liquid in glass thermometer using two fixed points. Okay. Let's look at conversation between two students. Okay. The boy said this thermometer does not have a clear scale, so we need another thermometer. But the girl said this thermometer can still be used. We just need to calibrate the thermometer. So a thermometer that does not have a scale can be calibrated using two fixed temperature points. First question, state what happens to the liquid in the capillary tube of thermometer when it is absorbed. So the liquid will expand. What does the length of the liquid column in the capillary tube indicates? Indicates the magnitude of the temperature. So the higher the liquid expand means that the temperature increase. Okay. First point. So calibration is a process of making a scale of reading on a thermometer. Okay. So we want to for example, the length between 1 degree Celsius to 2 degrees Celsius, how long? Okay, so that is the calibration. Okay, how we do the calibration? So we have what we call two fixed point. So the first one is 0 degrees Celsius, the fixed lower limit, that is the melting point for ice. Another one is the 100 degrees Celsius, the fixed upper limit, that is the boiling point of water. Now, the length of liquid column between the fixed lower limit and the fixed upper limit is divided into 100 equal division, because from 0 degrees Celsius to 100 degrees Celsius. And the thermometer is then calibrated and can be used to measure temperature between 0 degrees Celsius and 100 degrees Celsius. For example, the length between 0 degrees Celsius to 100 degrees Celsius is, let's say, 10 cm. Then we divide it by 100 degrees Celsius section, and one section is equivalent to 0.01 centimeter. Okay. Now, the process of calibrating uses the thermometric property of liquids in glass. So, thermometric property means a physical property which can be measured which change with temperature. For example, length of column of liquid expand when temperature increase. Okay. So, how a thermometer is calibrated? So, at the scale of degrees Celsius, two fixed temperatures are chosen. Again, we discussed just now. Lower point or ice point is the melting point of pure ice, that is 0 degrees Celsius. Second one is upper point or steam point, that is the boiling point of water at atmospheric pressure of 1 atmosphere. That is what? 100 degrees Celsius. Okay, so this is the instrument that we use to determine the ice point and also the steam point. Okay, so let's discuss in detail. So the first one, we have a beaker A. Okay, so the aim of our activity is to calibrate a liquid in glass thermometer using boiling point of distilled water and melting point of ice. So the apparatus. Okay, so the first one, we cover the scale of thermometer with masking tape so that the scale cannot be seen. So we will use ordinary thermometer with the scale. So we put the masking tape so we cannot see the scale. Now, the first one, we fill beaker A. So this is beaker A with ice and a small amount of distilled water. And then we put the thermometer into beaker A. Wait until there is no more change in the level of liquid column. So the temperature will rise up, right? So wait until it stop increase, and then what we do is we mark the level of liquid column on the stem of the thermometer and label this as 0 degrees Celsius. Right. Okay, so we label it as 0 degrees Celsius. Now the next one, we put another beaker B with distilled water, and we heat up with immersion heater. So fill beaker B with distilled water and put in an immersion heater. So and then we put the thermometer. So when the distilled water in beaker B is boiling, put the thermometer in beaker B. Wait until there is no more change in the level of liquid column. Next, we mark the level of liquid column on the stem of the thermometer. This level is known as 100 degrees Celsius. After that, we switch off the immersion heater, right? So now we have two levels. The first one is 0 degrees Celsius. The second one is 100 degrees Celsius. Alright, so we have like this level. So 0 degrees Celsius is the bottom point. 100 degrees Celsius is the upper point, right? So what we do next is measure the length of 0 degrees Celsius to 100 degrees Celsius, and we mark it as L100. For example, 100 degrees, 10 cm, right? Prepare beaker C. We have another beaker, and then we fill it with tap water with unknown temperature. So we put the calibrated thermometer into beaker C, and again we wait until there is no more change in the level of the liquid column. Then mark the level of the liquid column on the stem of the thermometer and label this level as theta degrees Celsius. Next, we measure the length of from the 0 degree Celsius mark to the theta degree. Okay, next we calculate the temperature of tap water using the formula theta equals to L theta over L100 times 100 degrees Celsius. So this is how we get the unknown temperature, right? Now, let us discuss a few questions. So question number 1. The bar of the thermometer should not touch the base or side wall of the beaker while taking measurement. I explain. Because we want to prevent heat loss through the beaker to the surroundings. Number 2. Why should you wait until there is no more change in the level of the liquid column before making a mark on the stem of the thermometer? Because we want to make sure that the thermal equilibrium state is reached. It means that no more increase of the temperature. Right, so this is how we get the length. So the first one, we have theta is the temperature of the liquid, unknown temperature. L theta is from here, the length of the capillary tube at temperature theta. L0 is the length of the capillary tube at ice point. So this one, from here to here, ice point. And L100, length of the capillary at boiling point. So from here to here, 100 degrees Celsius. So what we do is, we have the formula T equals to L theta minus L0 over L100 minus L0 times 100 degrees Celsius. So let's try to do one question. Now, what is the value of temperature T? So from here to here, this is L0, right? 3.6 cm. From here to here, 13.6 cm is L100. And 9.3 cm equivalent to the L theta, unknown temperature, right? So what we do is, we use that at 0 degrees Celsius, the length is 3.6 cm. At 100 degrees Celsius is 13.6 minus 3.6 equals to 10.0 cm. So x equals to 9.3, right? 9.3 minus 3.6, we got 5.7. Then we do mathematics. So x equivalent, x divided by 100 degrees Celsius. 5.7 cm divided by 10.0 cm, and we get x equal to 57 degrees Celsius. Or we can use the formula that we used just now. So the formula will x equals to 9.3 minus 3.6, right? 9.3 minus 3.6. 13.6 minus 3.6, and we got 57 degrees Celsius. Okay, same, right? Okay, so that's it for our topic. So let's discuss the formative practice 4.1 on page 124. Okay, first question. State what happens to the two objects in thermal equilibrium. So, final temperature of both objects are equal, right? Another one. Heat is transferred from object A to object B, and also from object B to object A with the same rate, and the net heat transfer is 0. Okay, the second question. Is our body in thermal equilibrium with the environment? explain your answer. Okay. Alright. Do you think yes or no? Yeah, the answer is no. Because the human body runs at a constant 37 degrees Celsius, but the air around you at room temperature is about 20 to 25 degrees Celsius. This means heat is constantly leaving your body to warm your surroundings. So our body constantly utilize energy that is obtained from food that we have eaten. So in producing heat that keep us warm. Only several hours after death will your body approach room temperature. At that moment, we are in thermal equilibrium with the environment. Okay, last question, number 3. We have the diagram. So Asha used an uncalibrated laboratory thermometer to determine the temperature of a liquid theta degrees Celsius, right? She finds that the length of the liquid column when the thermometer is put in the liquid is shown. So calculate theta. So what we have here is the top one, 4 cm. The 0 to 100 is 12 cm. So what you do is 4 divided by 12 times 100, and the answer is 33.33 degrees Celsius. Okay, so that's it for today. So we stop here. Thank you. Assalamualaikum and selamat sejahtera.